All right, hello everyone. Welcome back to the third talk in our mini course series on two seagull spaces with Julie Bergner.
Great. Yeah, thanks, Sarah, and thanks to everybody for coming back for round 3. Sarah was just asking me, I was prepared, and apparently I did not get my title written down on paper. So we've got a couple of things today. So one is wrapping up from last time. So this is more about this general S-dot construction. But then I want to move on and talk about Hall algebras, which is kind of one of the other central themes of two seagull spaces. All right, so let me recap a little bit what we did last time. So we introduced the S-dot construction and motivated why we care about this for the purposes of algebraic K-theory. And so we talked about this for an exact category or something a bit more general called a proto-exact category. And we talked about why that is a two seagull space. But then we wanted to talk about generalizing and giving sort of the most general input that you could feed into this S-dot construction and still get something two seagull. And we talked about how there are possible inputs, say categories with cofibration or Waldhausen categories, that may not be. But we didn't quite finish that. So we talked about this generalizing the input, but this was just for a discrete version, just to keep the abstraction contained a little bit at least to start. So what I want to do today is, so first of all, I want to go back to generalizing the original version, which is the one that really arises from examples and things that we care about. And then the second thing then is to talk about how to get Hall algebras from two seagull objects, which in some ways is a bit complementary to the S-dot construction. All right, so let's recall a little bit, in case there's anybody who wasn't here last time or just wants a quick refresher. So if we say we're feeding in an exact category, then we defined Sn of C to be the groupoid of diagrams of this particular form. Sort of triangular form here. Okay, so just to recall, say if we were in an exact category, we have some notion of admissible monomorphisms. Those are the things that are going horizontally. We have admissible epimorphisms. Those are the things going vertically. These stars are the zero object of our category. And we ask that all the squares be bicartesian. And so what we did last time is that we said, well, we don't need a common ambient category. We can work in the more general framework of a double category. So this is something with objects, with horizontal morphisms, vertical morphisms, and squares, satisfying some kind of compatibility. So what I want to do here is sort of go from the discrete version to what we might call the homotopy version. And so we talked last time about moving to a setting of a double category, and we want an up to homotopy version of that. And if you remember back in the first talk, we talked about seagull spaces or one Siegel spaces being homotopy space versions of categories. Oh, sorry. Is there a
Mas eu
question?
vou falar dessa parada aí, é útil. Mano, mas o que é útil não é.
Might just be somebody who's not muted. Yeah, okay, great. Okay. So the right homotopy version of a double category is a double Siegel space or a double one Siegel space. Okay, so what is that? So this would be a functor from the double part is this is delta op cross delta op into simplicial sets that is a Siegel space or one Siegel space in each variable. So if we say fix an object of this delta op and just look at everything at that level, we get a simplicial space and we want that to be a Siegel space. And similarly, if we fix something here and let this one vary, we want that to be a Siegel space. So this is something that we could call a double category up to homotopy. All right. So now we have these couple other conditions. So one thing we wanted for in our double categories, unlike up here, we don't have a notion of bicartesian squares if we're not living in a common category. And so we had this stability condition. And that said, well, in the discrete version, that said, anytime we have a span like this, or a co-span like this, then this uniquely, and in the discrete case, this really was uniquely, determines a square. Okay, and so when we pass to the homotopy version, we just say, well, it now determines a square up to homotopy, or you might say up to a contractible space of choices. So if we were looking at, say, an exact category, I mean, remember, these are supposed to be bicartesian. And so in that case, say you're taking a push out of this span, then that would be, unique up to isomorphism. And so that's the sort of thing that we want to be true here. So it's just sort of the homotopy version of uniqueness. And then we have something similar. So when we had, when things were pointed, so that meant that we had an object star that is initial for the horizontal category and terminal for the vertical category. So again, that's just because we always had the star, it's always mapping into things horizontally, and vertically things are mapping to it. And then so the homotopy version is just, again, you just want that to be space of such objects and the space of maps to and from other objects, depending on which category you're in. Those two spaces are contractible. Okay, just the up to homotopy version of uniqueness. And then we talked last time about the generalized version of pointedness, which is this augmentation.
Sorry, about the stability. Do you mean that
it determines a square that commutes up to homotopy, or do you mean that it determines a strict square that is unique up to homotopy?
So remember, we're in like a double category. So we're not talking about commutativity anymore. So well, all right. If we're in a double category setting, commutative squares don't make sense. It's just part of the data of the double category. So you want there to be, so if you say have this span, there's a unique, you have a unique square that is allowable in that double category. Now, if you're in a double Siegel thing, well, okay, now these are, maps in your bisimplicial diagram, but there's no sense of being up to homotopy. It's just, is it allowable or not? Is this a, in this case, a square would be living in what, like X of 1, 1. And like, is this an element of the set X1, 1 or not? And depending on what, but stability says, well, there is one and it's unique up to contractible space of choices. All right, and then remember we had this generalization of pointedness. And we have similarly when we do the augmentation. So that was where we had sort of this set of objects that have these same sort of local universal properties. And again, there's going to be, uniqueness up to contractible space of choices. Okay. And one way to organize this, if we have a double category, we think of this as being a bisimplicial diagram. If you're talking about, when you want to encode the pointedness, the augmentation, one thing we can do to organize this data is via a category, which we call sigma, which is, so this is given by adjoining a terminal object, a new terminal object. Sometimes we just write it as -1 to the category delta cross delta. And so this data can all be described. So we look at functors from sigma op to simplicial sets, and then restricting to delta cross delta op cross delta op, you look at, whether it satisfies the double Siegel condition, and then this extra object comes along for the ride too, and the image of this object -1 is what gives you your augmentation. So if it's a point or something contractible, then you're pointed. If it's more general, then you're augmented. All right, so now here's the more general theorem that I proved. This is the same group of co-authors as the result from last time, but a later subsequent paper. Okay. And I'm going to sort of put a lot of things into one theorem here. So first, I'm just going to go ahead for the people who are interested and phrase this in the language of model categories, and kind of ignore that part if that's not as familiar to you. So there is a model structure so this is the category of functors from sigma op to simplicial sets, whose fibrant objects are the augmented stable double Siegel spaces. And then the second part is where we bring in the S dot construction. So the S dot construction defines the right adjoint of equivalent equivalence between the model structure from part A and the two Siegel space model structure, which I discussed very briefly last time. Again, if you're not a model category person, just say there's some appropriate equivalence of homotopy theories between the augmented stable double Siegel spaces and two Siegel spaces, which is the appropriate homotopy generalization of the discrete version from last time. And then lastly, well, we really want that this S dot construction recovers the ones that were known before. It's not some new thing. And so on exact categories or proto-exact categories, or, you know, the quasi-categorical version of these, stable quasi-categories, lots of these things that we really like to take S dot of. This S dot recovers the classical, some of them are not that classical, they're still pretty new, but classical or known versions, which is what we would hope for. Okay, so that tells us indeed that these augmented stable double Siegel spaces really are generalizations of these other things. And so it does kind of give us the maximum input from which we can get something to Siegel. And I'll just comment on some related concepts that you might have heard of. There's been some recent work about what are called CGW categories and their variants. So the CGW categories were first defined by Campbell and Zakharevich. And there's also been some variants in a recent preprint of Sarazola and Shapiro. And these, in some sense, have a similar sort of motivation for their definition and existence, namely that they provide some very general input for K-theory constructions. So you can apply the S dot to these. You can also do, you know, other things, other ways that people get K-theory. But a natural question is, well, how does this fit into our story? And so some work in progress that I'm doing in collaboration with both Brandon Shapiro, with Shapiro and Ina Zakharevich, is, well, so what we know is that, you know, CGW categories can be understood by some kind of appropriate nerve-like functor as not just augmented, but actually pointed stable double Siegel spaces. And then, well, so that's the part that we know already. The second part is, you know, identifying sort of which ones they are. So they definitely form a subcategory. They're so we'd like to know which ones they are. And the hope is that this can inform sort of both ways. So some of the things that these groups of collaborators are doing with CGW categories, we can say, hey, can some of those be pushed further into, say, suitably general augmented stable double Siegel spaces, but also, you know, they've got lots of nice examples. For example, the K-theory of varieties fit into this framework. And so we could say, well, you know, we can understand those as nice examples of our framework as well. Okay, so that's where I'm going to stop talking about the S-dot construction for the moment. Are there any questions before I change gears?
Yeah, I have a question. I was wondering if you knew anything about the left adjoint and the equivalence.
Yes, I mean, in fact, if you read our paper, we actually look at the in some sense, the left adjoint is actually the one that's easier to work with. So it's given by some kind of functor between delta and sigma. It's actually quite nice. It's given by what we call it some kind of path construction. So you're using this kind of decollage type thing in each direction. I mean, I could give a whole nother talk on that. I'm not planning on it, but yes, we understand it in fact, the fact that it happens to be the S dot in some sense is secondary to the way we built it up.
Oh, okay.
Yeah.
Cool.
All right. So now I want to talk about Hall algebras. And I'm going to motivate these. I don't expect that these are necessarily familiar to people at all. So let me talk about just sort of their classical definition, why people say in representation theory care about them. So our setup is going to be that we're going to let A be an abelian category. And we're going to assume some finiteness conditions. So we're going to assume that all the Pom sets and all the extensions are finite. So for all objects A and B, and this is often what's called being finitary. And I don't know that I need it for this. Often it's assumed that these are hereditary and that they have no higher X groups either. Okay, so we can associate to this an algebra. So Hall algebra, which we write as H of A. So this is defined by, so first of all, as a vector space. So this is just, doesn't really matter. This is over just some field, little k. And we take as its basis the isomorphism classes of objects in A. All right, and then we need a multiplication. And so if we have an isomorphism class A and we want to multiply that by an isomorphism class B, this is going to be a sum over all possible isomorphism classes C of, well, C, but then we have some coefficient GCAB. And this is usually called a Hall coefficient. And what this is doing is, well, roughly speaking, it's counting the short exact sequences or the extensions of A by B. And the definitions of this vary slightly, but I'm going to use the one where we mod out by the cardinalities of the automorphism groups of A and B. And it turns out that, as suggested by the name, that this really does define an algebra. So this defines an associative and unital algebra. And I will comment that actually associativity is rather non-trivial to check here. But so here's an example of and why, I mean, these have probably been around for close to it's close to a century, but they became very interesting to people around the 90s for the following example. So we're going to take a Lie algebra, G, and we'll assume this is of so what are called simply laced of type A, D, or E. And well, the types kind of are described in terms of their associated Dinkin diagrams. And these are the things that are simply laced, which distinguishes the A, D, and E from the B's and C's and other kinds. So you don't have multiple edges and loops. So for example, the A3 Dinkin diagram is just this little graph here with 3 dots and 2 edges. And something you can do with this is you can say, well, let me make, this is just a graph. Let me make it a directed graph just by choosing an orientation on each edge. So we get, this literature is usually called a quiver. And so in this case, for example, we could just take those edges there. There are different choices here. All right, and so now I want to produce a Hall algebra, so I need an abelian category. So I'm going to let A be the category of representations of Q over a finite field. So for example, for this quiver Q, an example of a representation. So you're just mapping this into FQ vector spaces. So maybe you have sort of FQ 3 copies, and then maybe you have FQ cross FQ, and maybe you just have 1 here. And so these would be your objects of this category. Morphisms would be commutative diagrams. You have another one and you have maps between them. They commute, so just natural transformations. And this, in fact, forms a finitary abelian category. And the finitary comes from, well, the fact that these Dinkin diagrams are really simple. Again, we don't have any loops or anything happening there, and we're over a finite field. And so that means we get an associated Hall algebra, which we'll call H of Q. And now this does depend on some choices, like, what quiver did you take and so forth. I'm not going to go into any further details. This is a very quick crash course. But why people care about this, and why this became very popular in the 90s, starting in the 90s, is this has a close relationship with the quantum group associated to that Lie algebra. So UQ of G. And so this is this work of Ringel and Green. And I mean, roughly speaking, modulo, okay, what's happening with choices, it looks like sort of half the quantum group. The quantum group sort of has this decomposition into upper, lower, and middle pieces, and it looks like one of the pieces. And so people got very excited because people like quantum groups. So that was why this became of interest. So what does this have to do with two Siegel things? Now, as I understand it, in fact, for Dickerhoff and Kapranoff, finding a sort of a source of Hall algebras was one of their motivations for actually defining two Siegel spaces. So what I want to do is give a reinterpretation of some of these definitions that I just gave, because, well, I mean, if A is a finitary abelian category, that's a special case of, say, an exact category. And so a lot of the things that we've talked about prior to this would apply to it. For example, we can apply S dot to it. So we can take the S dot construction of it. This is a, well, as originally defined, it's a two Siegel groupoid. Or we can take nerves of those groupoids to get a two Siegel space. And again, just to emphasize things we talked about last time, so S0 is going to be the groupoid of zero objects. S1 of A, so this is just the groupoid. This is the groupoid of objects. And so, well, it's a groupoid, meaning you just have maps between objects when they have isomorphisms between them. So this is a groupoid whose components, connected components, are corresponding to the isomorphism classes of objects. And then, again, as we talked about last time, S2 is going to be the groupoid of short exact sequences. And you can keep going and describe the other ones. And this is two Siegel. So recall that composition, such as it is, so this was defined via the span. So we have, well, we have two one simplices in this case, because S0 is contractible. I'm just gonna be sloppy and I'm gonna omit it from the notation. Basically, we just get the product over here. And here we have S2, this map was D0, D2, and then we had the map D1. Okay, now, so this elements here look like short exact sequences. And if we take D0, D2, then this is going to look like the pair BA. Oh, actually, let me write it. Let me rewrite this as D2, D0. Goes either way, but this actually matches with my notes. So I have AB, and then this map is going to go to C. This is D1. This is going to pick out the middle piece. Okay, now this map, so by assumption, by our finitary assumption, this map has finite fibers. And that's partly, this is coming from this X1 condition. And well, we also have, the Hom set and in particular the automorphism groups of A and B, if we're trying to think of that Hall multiplication making sense. So remember, the composition was defined by saying, well, let me take a pair of objects, A and B, and look at, well, in this case, the different choices for composition are going to be all the extensions. So this is starting to look kind of like our Hall multiplication. So if we take a field, K, we're going to take finitely supported functions from, I'm going to take pi 0 of S1 of A. So this is just your isomorphism classes of objects to the field itself. And so now this is going to define a K vector space. So I'll just write it as K to the pi 1 S1 A. And I mean, this is actually just, an alternative way to describe the vector space that I described before. I mean, you can either take finitely supported functions into your field, or you can just take the vector space spanned by your isomorphism classes of objects. Comes down to the same thing. Okay. And now we're going to use this composition to define a multiplication on this vector space. So if we want a multiplication on this, so we want to input two elements of this vector space. And well, observe that this product algebra is isomorphic to where if I instead took functions from product of pi 0 S1 of A with itself, and then mapped that into K. And now I can take the induced map to, now this will be maps from pi 0 S2 of A. So this is just going to be the pullback along this D2, D0. So just take this map and then say, well, okay, now map that into K. And then I can take a push forward along D1. Oops, sorry, that's a 1. And then a push forward along. Back down to the, sorry, pi 0 S of A. And again, some of our finiteness assumptions are guaranteeing that this push forward is going to be well defined. So what happens here? So if I have a function f here from this product into K, then what's going to happen when I apply these two things? I'm going to get the function that inputs. So this is going to be another take something in here that's an isomorphism class of objects in A, and it's going to go to the sum over all, well, I'm going to let S be short exact sequences as before, where, well, the extension or is C, or D1 of S is equal to C. And then I will get, so for each of the such choice, I will get, well, this is F of D2, D0, and then apply that to S. Okay, but then this should just be F of AB, because D0 of S should be A and D0 of S should be B. All right, so we want to convince ourselves that this recovers this Hall multiplication that we had before. So if, let's take F, I've been sort of ambiguous where this lives, but let me think of it here. I want to think of F as being the pair. So I want this to be this characteristic function that just goes to, goes to 1 at the object A or any of its isomorphic objects, and then 0 everywhere else. Similarly, I have the characteristic function on B. And if we feed that into here, we get, I'm going to break this up a little bit here. So I get a sum over all choices of C, and then sum over all short exact sequences. I'm going to write it out. Of the characteristic function of C. Well, if I count how many of these there are, that's going to recover this coefficient that we had before. So this should just be the sum over C, GC, AB, and then times, that's your coefficient of the characteristic function associated to C. So this recovers effectively the definition above. So we sort of rerouted our definition by saying, all right, we had this finitary abelian category. We take its S dot, we get something two Siegel, and then we can use the two Siegel structure to define an algebra, and that recovers the Hall algebra that was already known. Okay, so we can do this pretty generally. We can't do it for all two Siegel spaces because we need some finiteness assumptions, you know, in order for these sums to be defined. But for the same kind of construction, so sufficiently finitary, by which it's just kind of my way of saying, all right, all the things so that the summations that we need to be well-defined are well-defined. And so two Siegel objects, X, and we need them, well, for at least to get an algebra, we need X0 to be a point. Now, if you drop this assumption, you don't get an algebra, you get a K-linear category. So it's a perfectly good thing to do. You just get something more complicated than an algebra. All right, so let me, as I've kind of been doing here, I mean, this is fairly general. Let me again take a step back to the discrete case, to two Siegel sets, and tell you just very explicitly, because this has a pretty short definition. Well, I mean, shorter than the process I just described, at least. So let K be so again, I want a reduced two Siegel set, so that's just this condition. So K0 will be a point. And let little k be a field. So the Hall algebra, we'll usually just write this as H of K. If I want to emphasize the field, I can put that in a subscript. So this is defined as, so first of all, this is the K vector space of finitely supported functions from the one simplices of the simplicial set, of the two Siegel set into little k. Again, you can also just as easily think of this as just the K vector space spanned by the elements of K1. And then the multiplication, since I've written it as functions, let me use the function, the characteristic function notation. So if I have the characteristic function associated to some element little a of K1, and I multiply that by the one associated to B, then this is just going to be a sum over other elements C of GCAB times the characteristic function of C. And now, again, I'm defining this in terms of a two-Siegel set, not in terms of something like an abelian category, but we can describe this just fine in that setting. So this GCAB is the number of two simplices so say Z in K2 such that, so D0 of Z will be B, D1 of Z is C, and D2 of Z is A. So pictorially, it's a two simplex where you have A and B and C. And then if this, like our previous example, is coming from like an abelian category, then this is just what we had before, because remember our two simplices correspond to short exact sequences. But we have this more general definition. Okay. Now, so just a couple of notes or remarks. So the construction that I described before for abelian categories, we more naturally had a two-Siegel object in groupoids, and then we just sort of took isomorphism classes of objects. And we can do that here. So we can recover the above classical example using isomorphism classes in two-Siegel groupoids. So you just apply the isomorphism classes so you get in a context that looks more like this. There are also other flavors of Hall algebras, and you can also recover them, again, using different kinds of two-Siegel objects. So you have variants like derived or motivic Hall algebras. And I'm not going to say anything. There's a lot of, this is in the higher Siegel spaces manuscript of Dickerhoff and Kapranoff, and I will refer you to that. It's a really beautiful theory. And if you're saying, well, I really don't like taking isomorphism classes, can I keep more of that data? You can. And again, Dickerhoff, Kapranoff do this. You can retain more structure to get, well, if you're not reduced and you don't want to take isomorphism classes, you can get a Hall infinity 2 category. So that's a whole nother story and much more complicated, but again, a very beautiful theory. So let me give an example. So we've had this running example through this series of partial monoids. So let's look at what happens if we apply this definition up here. So if we take its Hall algebra, so as a vector space, this is just spanned by the elements of M. Remember, M itself if we thought of a partial monoid as a two-Siegel set, as a simplicial set, the one simplices were just the elements of M. And now if we take a multiplication of two of these elements, so say we have an M and excuse me, we have an M and an N in our partial monoid, well, these might be able to be multiplied or they might not. So I claim that this multiplication will be M times N if such a thing exists, and that was true if M and N are in this set, M2 of allowable composable pairs. And if not, then we just get 0. And so this is not a terribly interesting algebra. And this is happening because, well, in this case, composition is unique when it exists. So there's no multi-valued composition. It's just only partially. It's just sometimes it's defined, sometimes if it's not, and if it is defined, it's unique. And so that's so there are no sort of longer sums. So you would get sums when, you know, you have two different possible composites for A and B. That's how you get multiple two simplices. And you get interesting coefficients when you have multiple two simplices with the same boundary. So when you would have like the same composite, but it's sort of the composite in two different ways. That's how you get interesting Hall coefficients. And we don't have either of those things here. So there's no longer sums or interesting coefficients. They're either 0. Okay. Now, in fact, both the examples, so I mean, this is kind of in the running example, but in the first lecture, I also talked about this example of this sort of cobordisms with genus constraints. And both of these fairly concrete examples are ones where composition is unique if it exists. Now that's not true for the S dot construction, but what I want to do, I want to just start to introduce another example here in the last few minutes, and with the idea of talking about its Hall algebra, because it's a little bit more interesting, but I think I won't get to actually talking about the Hall algebra until next time. So, and in general, this is just kind of a fun hands-on example of a two-Siegel set that you can really play with. So let G be a finite graph. And I claim that you can define an associated simplicial set. Well, the claim is this is eventually going to be two Siegel. So again, I will decorate this with a G when I want to emphasize the graph, but often mostly just call it X here. So X0 is always just going to be a singleton that I'm going to denote by the empty set. X1 is going to be the collection of subgraphs of G. So that sort of explains this. This is going to correspond, its degenerate one simplex will just be the empty subgraph. And then Xn for higher n, these will be subgraphs H of G that are equipped with an ordered partition of the vertices of H into N, where that's that N, possibly empty subsets. Okay. So, I actually cheated and pre-wrote out this because it takes a bit to draw. So if we let's take just this simple example. This happens to be the same as the Dinkin diagram we looked at earlier, no particular relationship here, but just this little graph with 3 objects and 2 edges. So in this case, well, x0 again just has this 1 point that we think of as the empty graph. X1 are all the subgraphs. So we have the empty one, we have the 3 singleton vertices. We can take pairs of vertices, so we can take A and B and either include the edge or not. Similarly for B and C, A and C doesn't have an edge between it, so we just have one subgraph with them. And then we have the 4 subgraphs with all 3 vertices, just depending on which edges we want to include. So we can include all of them, none of them, or just one of them. And now this is where things get interesting in X2. So we have to partition the vertices and so into an ordered, I think, yeah, so this was an ordered partition. I find it easier to depict with pictures, so assume that blue comes before pink, that's the ordering. If I have the subgraph, if I have the empty subgraph, well, I can partition that either way. The simplicial identities will tell you that these are the same. If you have just a singleton, the only possible partition is just, well, make one of the sets in the partition to contain that vertex and the other one to be empty. I have 2 choices. If I have 2 vertices in my subgraph, well, I can sort of lump them together and then take the empty thing, or I can choose one vertex or the other. And then, well, if I have something with 3 vertices, then I start having a lot of choices, and this is all of them. And then if I have a 3 simplex, well, the 3 simplices, okay, this is going to explode even more. So again, I could sort of lump everything together and have a couple empty things in my partition. Oh, it looks like I forgot to color this one. This one should be purple. And I'm just saying purple is what comes after pink. So these are the various things that you can do. So let me just quickly describe the simplicial structure here, because I haven't done that. So if I want to look at the face maps, so let's just look at, say, what the face maps from X2 to X1 would do. So here's an element of X2. So let's do the 2 simplex here. And so this is because we have an ordering, we do sort of the usual things. So D0 would say, well, just leave off the first part of the partition. For the first part is the blue part, so we're just left with the pink part. We'll get that subgraph. D2, we leave off the second thing, so we're just left with the subgraph that's circled in blue. And then the D1, you just merge them. And so you just forget about the partition in this case, and you just get this subgraph. And then the degeneracies, so let's say from X1 to X2. So if I took, for example, this one simplex, this subgraph, the degeneracy maps are just given by inserting an empty set in our partition, and which degeneracy map you use tells you which comes first. So for S0, you say, well, make the degeneracy come first. For S1, you say, make the subgraph come first. And so that's the simplicial structure. I don't have time to explain why this is 2 Siegel, so maybe I'll start next time by talking about why it's 2 Siegel, but it's not 1 Siegel. And then I'll talk about then, you know, how to look at some of the different constructions that we've done, including Hall algebras, with this particular example, and see what we get. So that's where I'll start for the 4th talk on Thursday, and I'll stop there.
All right, let's thank Julie for the lecture.